we'll go into the object-oriented industrial programming, what it is, why the term was coined, how it's different than traditional object-oriented programming, and how it can be used to make the industrial controls programming much quicker to create, easier to understand, and easier to maintain. It will cover the central configuration service that enables this technology to work. We'll also talk about object-oriented industrial visualization, which is the visualization side of object-oriented programming. And then we'll touch on some simulation if we have time and talk about some other resources. So you'll quickly see that I'm a huge advocate of object-oriented industrial programming. I believe it to be the future of the industrial controls programming, and I believe that those who embrace it first will be the first to gain the competitive advantage that it provides. So when I go out and ask programmers, what is object-oriented programming? I tend to get two very different answers. Someone from an IT background, they're going to talk about classes, inheritance, overloading, polymorphism, and all that kind of thing. Somebody with an OT background is more likely just to say something simple like, well, creating function blocks, or creating function blocks and declaring function blocks inside other function blocks, or something like that. So to keep these two interpretations straight, I use the IT definition for object-oriented programming for the IT side. And I use this new term, object-oriented industrial programming, for the OT's definition of that. So these are characterized by, object-oriented programming, and I should also, before I go on, mention that CODESYS supports both of these just fine. This chapter, we talk about object-oriented programming. I have a whole nother chapter that talks about the full suite. So it does support both. It does a great job. So anyway, traditional object-oriented programming is, traditionally text-based, C++, C#, Java, Python, those type of things, typically text-based. Again, uses all these features and functions at their disposal. Typically requires quite a bit of training. You're going to typically have a 4-year computer science degree to be able to really master object-oriented programming. And oftentimes plant managers, I have find it to be too complicated for their plants. It's too complicated for their plant technicians or their electricians to understand and modify and maintain and so forth. But it is great for libraries. So object-oriented programming works well for the libraries, for instance, that CODESYS created, because CODESYS has a couple buildings full of highly skilled, highly trained computer scientists. So the libraries, CODESYS uses full object-oriented programming quite a bit for all the libraries that they create, and they work great. On the other side, object-oriented industrial programming, the IT definition, this is going to be primarily graphics-based. It's a lot of PLC side came up from ladder logics. They're very used to graphics-based. Seems to me engineers tend to be more graphically oriented. So the graphics-based languages are a little more popular. Ladder, CFC, which is a superset of function block diagram, and of course, sequential function chart. We'll talk a little bit about those. Object-oriented industrial programming only uses a subset of the object-oriented programming. It only uses encapsulation, composition, and abstraction. And we'll talk about all three of those in a few minutes. Because we only use this simple subset, it's very easy to master, very easy to understand, and can just do on-the-job training. It doesn't require university type of training. Everyone that's tried it that I know of embraces it and loves it, and it's great for programming. So basically, object-oriented programming gives you the productivity of object-oriented programming without all the complexity. So it's a great subset. We'll talk about that in much more detail. But first, let's go back in history a little bit. These next two slides are actually from a different chapter, but you really need to know this to understand object-oriented industrial programming. Function blocks is what really makes this possible. So I want to just make sure we all have an equal understanding of function blocks before we move on. So originally, we created a program for to control a pump. We'd write a program, we'd create some global variables, we'd write a program, we'd use those global variables, and we were happy. Okay, but then we needed to control 2 pumps. So what would we do? Well, then we would go in and duplicate the global variable list for each additional pump, come up with some naming convention to differentiate the global variables for each pump, copy that pump into another program, go into that second program, and go in and rename all the variables to those new variables that use that naming convention. Of course, then the next thing we do is figure out why it doesn't work because we forgot to do something, or worse yet, a few months down the road, we get a call at midnight, something doesn't work because some aspect of it we forgot to update, or if we updated a bug in the first control program, and we forgot to go in and do it in the second one. And of course, the third one, you got to go through that whole process again. Go in the global variable list, put in some new variables, rename them, do your naming convention, copy the program, go into the program, rename it. And I know some people have created some spreadsheets and some automation to try to help with that, but it's the new function blocks in an IEC 61131-3 really is the best solution. The way this works is very simple. We just create a function block, use this programming, put it into a function block, take all those global variables, put it in the function block itself, and then we can create 3 instances of that function block. So just like we can declare 3 instances of an integer, we could say integer 1, integer 2, integer 3 of type integer. The same way, we can just declare 3 instances of a function block, pump 1, pump 2, pump 3 of type pump control. Boom, we're done. That's all it takes. No copying global variables, no renaming global variables, no global variable naming convention, no copying programs, no having code in multiple places, forgetting to update it in one place and not the other. We're done. If we want 100 pumps is easy. Just put it into an array of 100 pumps. Boom, you got 100 pumps. Now you're going to ask me, what if these pumps aren't all the same? Very good question. We'll deal with that, and I'll show you exactly how we deal with that in the object-oriented industrial programming world. All right, one more slide. Let's just drive this home one more way using analogy with my favorite automobile, the 1964 Ford Mustang. So a 1964 Ford Mustang is a vehicle type. It's a specification. In CODESYS, the corresponding to that is a function block. It's a specification. You cannot drive a 1964 Ford Mustang specification. You can't drive it. You cannot run a function block. The Ford must first make one for you, and in CODESYS, you must declare one first. Ford uses a work order to tell the factory to start assembling the parts and putting things together. In CODESYS, you declare it. Again, we declare my Mustang. It can be any name you want to name it, of type Mustang. So this, just like the factory starts assembling things, this one, the compiler starts putting together memory and whatever's necessary to create an instance, they call that. If you're not familiar with that term, I'm going to use it a lot. It's an instance. So declaring an instance of Mustang. And the instance name is my Mustang. And it's also referred to as instantiating an instance of my Mustang. Now, and so now we've got that instantiated. Now we can actually call it. The factory has actually built one. We put it in our driveway, and now we can drive it. The factory can build multiple instances of a Ford Mustang. We can declare multiple instances of a Ford Mustang. Here I could say my Mustang, comma, my wife's Mustang, comma, my girlfriend's Mustang. Now, that last one you might want to keep secret, but that's completely up to you guys. None of my business. All right, object-oriented industrial programming simplifies the design of your plant or equipment and makes it much easier and much more likely to reuse control objects on future designs. Your plant or equipment is made of objects, motors, actuators, sensors, whatever. The control of your plant or equipment should be made up of objects too. So just as a motor is a completely self-contained object which does not require assembly or modification, the control for that motor should be a self-contained object which does not require assembly or modification. In software terms, this is known as encapsulation. Everything that is required to control a motor is encapsulated inside that motor control block. Just drop it into the design and it works. Just as a plant or equipment designer doesn't need to be an expert at motor design to specify and install a motor into his plant or her plant, the control designer doesn't need to be an expert in motor controls to configure and use the motor control block. Just drop it in, configure it, and use it. So reusing control blocks in your control code should be just as easy as reusing physical equipment in your plant. Physical equipment objects are specified, purchased, and installed. Control objects are placed, wired, and configured. The thought process is the same, and in fact, both can be done in parallel. In fact, I envision a future where when you get a pump shipped to your plant or a motor shipped to your equipment, it'll come with a memory stick or whatever happens to be in the future that includes the function block for that. So the physical equipment manufacturer will supply the function block for that piece of equipment. Now I've been asked, where does it make sense to use object-oriented industrial programming, or maybe where it doesn't make sense? So it basically makes sense to use anytime you're using multiple things. So if you were writing a PLC program that only ever ran one pump and that's it, well, okay, it might not make sense. Or if you're making a CODESYS program that was just getting data from somewhere and sending it somewhere else, that wouldn't make sense. But anywhere where you use multiple things, multiple motors, multiple valves, multiple actuators, multiple displays, multiple whatever, then it starts to make sense to do this. So I would say it makes sense most of the time. Oh, I've also been asked, is there a performance difference? Well, there's really no performance penalty. And the only performance gain that you're going to get is the fact that things are much more organized and you can go in and optimize things. I remember back in the old days when the argument was, well, I want to use assembly language because it's faster than compiled code. Well, yeah, that's true. But the fact that you've got compiled code and it's something that you can actually read and you can go and improve, it didn't take long before the compiled code to actually run faster than the old assembly code. So it's kind of the same concept there. So let's start in the beginning. Let's take a little walk down memory lane here. So back in the beginning, we're talking in the 1970s when we wrote PLC code, whatever language it was in, C or Pascal, I think was more popular at the time, or Fortran or whatever. Everything was pretty much flat. We didn't have much memory to use, space to use, and there wasn't a lot of functionality to carry out. It was just basically flat. We'd read the input, scale, perform any alarming that was necessary, do the control, and do the same thing on the output side. Same thing in ladder. Later on, we did get functions, which allowed us to do some structuring, but it was, essentially it was still flat. Later on, that flat programming technique gave way to a task-based approach, which was made up of a number of programs that each perform a certain slice of the operation. So there would be a program to read the inputs, another program to scale the inputs, another program to filter the inputs, another program to do any alarming, another program to do some control, another program to do this and that. So, a central characteristic of the task-based approach is a number of lists and processes that must be maintained. For instance, in a task-based approach, the control design is completed first, then the alarm manager is added, and then the persistence manager is added, and then the log manager is added, and then the visualization is added, and so forth and so on. And if you ever have to add something, if you add another input you need to add, or some more functionality you need to add, you've got to go back and add it to all those lists before you're done. And hopefully you don't forget, because it's an very easy thing to forget. The centralized task approach was a big advancement over the flat approach, but it suffered from the need to modify each new member, as I mentioned. And it just made it difficult to see the whole flow of information and understand the cause and effect relationship in that control code. These drawbacks made programming more difficult to design and more complicated for plant technicians to maintain. Now, object-oriented industrial programming turns that task-oriented approach basically on its side. So instead of all the functions being spread out amongst many new tasks, the functionality is contained inside each object. A single object performs everything that's associated with that input in this case. It reads the input, scales the input, filters the input, does all the alarming on the input. And then when you need another input, you just create another instance of that object, another instance of that object. So you're just reusing the same object each time. It's totally self-contained and totally self-reliant. Just add another object and you're done. You don't go back to these lists and add it to this list, add it to this list, add it to this list, forget to add it to this list, and so forth. Let's look at this again with another motor analogy. So the object behind object-oriented industrial programming is to encapsulate all the complexity into the object and then to abstract away that complexity into hierarchical levels where that complexity is necessary. So encapsulation allows objects to be created which contain all the functionality and the data necessary to control its matching plant object or equipment object. The user doesn't need to know or understand the underlying implementation, they just use it and it works. A good analogy is this car engine. The engine encapsulates pistons, valves, bearings, and a bunch of other objects and complex functionality. But the driver doesn't need to know how the engine works. They only need to know how to work with its interfaces, in this case, the accelerator pedal and the start button. Abstraction is where the detail is grouped by level in the hierarchy so that the programmer only needs to deal with a relevant level of complexity at any one level of the design. So, and composition is where objects are instantiated in other objects to build and logically partition a large hierarchical system. And then, of course, the interfaces provide the standard means for one level to interact with the next level in the hierarchy. So in this Mustang analogy we saw earlier, the Mustang has an engine, which has a starter, which has an armature, which has some copper wire, which is mined somewhere else around in the world. So this abstraction allows you to leave the complexity of the engine and the mining of its copper to others where that level of detail is appropriate for their level in the hierarchy. So fortunately, to be able to drive a car, you don't have to know how to mine copper. Or better yet, the engineer who has specified this engine, he doesn't have to, or she doesn't have to know how to mine copper either. That's pushed down to the lower levels of the hierarchy. Same thing is true, and you'll see this in some designs I show you. We use composition, remember, to put function blocks inside other function blocks. We keep the function blocks fairly simple, and we keep constant levels of detail in each one of those function blocks. So they are easy to understand, easy to test, and just make a lot of sense. All right, so what does a controls object look like in real life? So let's look at this example of an analog input that was provided by Coherent Technologies. This block encapsulates all the functionality of an analog input, including scaling to engineering units. That's the first thing we always do, scale to engineering units and use engineering units throughout the rest of the design. The clamping to engineering units, that's optional. And then some filtering, zero cutoff, so we're not totalizing noise, HMI override in case the sensor fails or something, rate of change alarming, and then the high and low and high, low, low alarming. So the programmer now only has to configure these objects and use their outputs. So you'll notice here we've got this analog output has two outputs. You can always tell what is intended to be used by the programmer because it'll always have an underscore PO at the end of it. We'll talk about that naming convention later. This one has two outputs, unfiltered output and a filtered output, so you can use either one. It has a number of configuration inputs. These are all with a CI. We'll show you how those all get set so we can configure this analog input for whatever application it might possibly need. Got some scale inputs. You'll also see some visualization inputs. These are meant to be connected to visualization or visualization outputs that are expected to go out to the visualization or the alarm manager. This naming convention, by the way, I had an interesting experience of not too long ago where I was working on a project. I was doing the control side. Somebody else was doing the HMI side. And that person told me that he has never, ever worked on a project where he didn't have to constantly ask the controls engineer questions on where to hook things up. It was obvious to him. So we used this hierarchical approach. He knew that there was a motor that was somewhere off in this part of the plant and he would just follow that full path name to get to that object. And then he'd look for the VIs, the VOs, and then it was obvious where to hook up his visualization. Anyway, so what does this look like in a real plant design? This is the same plant, courtesy of Coherent Technologies. So you notice that objects for the controls can be designed to correspond to the objects in the plant in such a way that they look very similar to the design. So notice a one-to-one correspondence. So here we have a temperature sensor, a pressure sensor, a horsepower sensor, and a level sensor. So we got 4 analog sensors. So we have 4 analog inputs. These are the same inputs that you just saw on the previous slide. And notice the naming, they're named the same. The horsepower 1, temperature 1, pressure 1. Okay, just a one-to-one correspondence between the actual PNID and the inputs. On the output side, same thing. We've got a motor, a pump 1. It's a reversible motor, so it's a reversible motor object with that name, pump 1. We have a variable speed drive for the mixer, variable speed frequency drive for the mixer. We've got a couple of valve objects, And then this one was interesting because we actually have a human object. I hate to objectify humans, but yeah, it's just another cog in the wheel. So this block would, the control says, okay, it's time to add some ingredients. It signals the operator through the HMI. The operator goes out and dumps the material into the hopper, comes back and says it's complete, and the control code goes on. Anyway, so the object of object-oriented industrial programming is to build a completely self-contained, self-reliant objects which can be used without any additional programming, such as adding variables to global variable list, adding alarms and all that kind of stuff. Just add the block to the design, connect its program inputs and output pins, configure its parameters, and just use it. The beauty of this approach is that encapsulating all of the functionality in an object is that the object can then itself be used as a building block. This is illustrated in this graphic where we see the mixer program from the previous page is now converted into a reusable object and then used to make a 3-mixer plant. If the individual mixing tanks are not identical, then the configuration inputs are added to modify these behaviors, and we'll talk about that a little bit later. So this is kind of analogous to building a high-rise building. The single mixing tank is the first floor. It represents a firm foundation onto which you can build the next floor, the 3-mixer plant. This could then become the firm foundation onto which to build the next level of plant. In this way, the plant of any complexity can be built, just as the high-rise can be built. And since each object is self-contained and self-reliant, the complexity remains constant as a program grows instead of growing exponentially as it does with the traditional programming. All right, so here's another example. So this is a material handling system. It had an elevator module, 3 conveyor modules, 2 offloading modules. And this particular plant only has 1 level of block diagram. The more complicated plant is going to have several levels of these. Eventually, you're going to get down to what I call the control and equipment diagram. This is where all the input objects, all your sensors, discrete inputs, in this case, are proximity switches. On the left, the outputs of those feed your control block, and the outputs of your control block then feed your output pieces of equipment. In this case, they're motors. And the beauty of IEC 61131 and CODESYS is they give you lots of languages. You can use the best language for the job. In the case, anytime you're doing block diagrams, CFC is the best design. Anytime you're doing block-based design, CFC is the best, in my humble opinion. But when you're doing anything that involves a state machine, anything that has any discrete feedback, a sequential function chart is the best choice. Anytime you're doing simple combinatorial logic, ladder logic is a good choice, and structured text for basically everything else. So now we're going to switch gears here, if I can. I'm going to just give you a quick little live demo on some of these. And somebody tell me if you're not actually seeing this. So we're going to look at a couple of object-oriented industrial programming designs. We'll start with this discrete process. So we're just going to take a look at it. So this is what you just saw before, the elevator module, conveyor modules, and so forth. So we're just going to double click on this elevator module. Now you see the control and equipment diagram. This is exactly what you saw. The proximity switches on the left, the motor controllers on the right, and the control in the middle. And this one, I can actually go online. We can run this one live. These all have their own simulator built in, which I'll show you in a moment. So we can actually look at the control code running here. It's a sequential function chart. Now those inputs that we saw here, right? All the inputs are the transitions. They drive the transitions. And then the outputs are all in these entry actions, and they drive the outputs. Each state drives the appropriate outputs for that state. And this one has a parallel sequence, so they actually have 3 different state machines going on simultaneously. Now let's take a look at, let me show you just a simulation module. I'm a huge advocate of simulation. I got a few more slides on that later on, but while we're here, I just want to show you so that we have. So, you'll notice, first of all, that generally speaking, I have 2 tasks, and one of them's for the plant, and the other one is for the simulation. That way I can easily take this out when it's time to map in the physical I/O, and just take the simulator out. So the simulator is, I've heard it also referred to as a digital twin. So this is basically the digital twin of this particular plant. It's got a little built-in self-testing system here. That's a sequential function chart that just sets up a test, performs a test, sets up the test. That's if this is set to false. If it's set to true, it's just running in its normal mode. And then we can look at one of these simulators. What's the elevator simulator made of? Well, the elevator has a conveyor coming in, and an elevator pushes it up, and then an elevator goes off, and a pusher that pushes these things around. So got a bunch of motors, motor simulators, very simple. We've got a conveyor simulator, got an elevator simulator, just a little bit of structured text that takes the amount of time it takes for the elevator to come up, and then flips that proximity switch. That's as appropriate. One thing I do want to point out here, so now in the simulator, the outputs of the control code are the inputs of the simulator. So these are the same full path names that you will use to map the IO into this. This would be an output into the simulator. And then the outputs of the simulator are the inputs of the control code. So again, this is the same full path name that you will use to map the physical input, this discrete input, into the control code. And then so when you're ready to flip over to real life, you just disable the simulator, map in your own IO, and boom, away you go. Let me show you another one offline here. Let's just show you this one, continuous process with let's continuous process with multiple reactors. Let's look at this one. So this is now, and now this is also showing you the beauty of 61131. I don't need a different language for doing continuous process. Same language, same tool, same everything. I don't need to learn two things like we used to in the old days when we had discrete languages and continuous languages. Nah, don't need that anymore. So this is a 3 reactor tanks that are all in series. So this reactor tank fills up and then it dumps it into this reactor tank, then dumps it into this reactor tank. So this is the complete controller design and the recipe controller. This customer wanted to keep all their recipes secret on their control device. So the recipes are all down here. The only thing that gets served up to the HMI is the names of the recipes. And then they can choose which recipe they want to use. That's what the recipe controller is for. So we'll just push into one of these, and then now we see the control and equipment diagram, same thing you saw before. Got some inputs, a level sensor and a temperature switch. It's got some outputs, 3 augers, an agitator, a heater, and a pump. Now this particular one, we don't know the flow rate coming in. The pump is just going to pump at whatever rate is necessary to keep this reactor tank at its level. And then these augers all need to run at a variable speed, depending on the flow rate that's coming in or going out. In this case, they're going to run at a variable speed. So if the flow is high, these augers need to run faster. If they run slower, the augers can run slower. So let's make this our active application, and we can go online with this one. It's got a simulator also, which I'll show you in a moment. And okay, then we're going to start off kick off a couple of traces. Got a trace, and I always just keep, these are the same traces I use for doing the system qualification and debugging. I just always keep them around in a trace folder. And then we can get this thing off and running. And it takes a little bit. It actually goes through this flushing process. So it empties the first tank, then it empties the second tank, then it empties the third tank, and then it fills them all up and it empties again. So it goes through a little flushing process. And while it's doing that, I'm going to, let me just give you a little quick look of the simulator part of this. It's going to look a lot different because, well, this part's going to look very similar. Basically, we have the same thing, reactor simulators. Notice it just has a sim at the end. So these are simulators for each reactor. It's got a little process here. This is the one that I told you about that simulates the operator choosing recipes and things like that. We can go in and look at the simulator, and it's got a tank simulator, and 3 auger simulators, and a heater simulator. What does the tank simulator look like? It's 4 lines of code. The tank is an integrator, right? So you have to integrate, remember your calculus. So the current level is the old level plus the difference in flow, the inlet speed minus the outlet speed flow times dt. That's it. Then we do a little clamping here so we don't overflow or underflow. And normally I'd put a pop-up error here if the tank overflowed or something, or the tank ran dry or something like that. But just for simplicity, that's all we've got here. And then, an auger simulator. So an auger simulator, what it has to do is it has to take the speed of the variable speed drive and put out pulses that are proportional to that speed of that variable speed drive, and taking into account the configuration constant for that auger. How many liters per rotation, or how many pulses per rotation of that auger. That's about it. So let's go back and look at our system here and see what it's looked like. Yeah, so we went through the flushing process. So here's this is the first tank, the second tank, and the third tank. And then this is the inlet flow rate. So it goes into a constant speed flow for a while, and then it goes into this random flow just to make sure our control loops are all working properly. And yeah, they're working properly because now the variable speed drives are all varying their speed with respect to that motor. And then we can look at a reactor. It's a single reactor. We can see that these are the pulses coming out of the augers. We can see that as the flow rate changes, the auger speed, the rate of the pulses coming out changes. So we can see that it's all working properly. So, and then, we can show you one other quick one here. Let's look at 100 reactors. Just go offline here. So let's say we got 100 reactors. What does that look like? Well, in this one, we did the first 3 reactors just to show this was similar as the previous one. Then we got one block here that's 97 reactors. And what does that look like? Well, it's just an array of 97 reactors, number 4 through 100. And then we need to hook them together. We do that here, which is the 5th reactor connects to the 4th reactor, the I-1. And the next time, the 6th one will connect to the 5th one. And boom, there we go. Now you can say, well, what happens if all these reactors aren't the same? Or they're different size, or they're different flow rate, they're different size augers that have different number of pulses per rotation and things like that. No problem. We'll show you how to deal with that next, I think. All right, so let me switch back now, back to the presentation, which I believe is this one. Hopefully you're seeing the presentation now. And to be able to reuse objects, it's no longer possible to use hard-coded global variables. Global variables just don't work with object-oriented programming or in either flavor. So the new techniques must be used to map your I/O and to set your configurations. You can't hard code them anymore. So what does that look like? Let's look at this example. So here, this is very similar to what you just saw. We have 2 reactors, reactor 1 and reactor 2. These are reusable objects. A reactor consists of a control system, and in this case, just 2 augers, auger 1 and auger 2. These are all reusable objects. An auger consists of a shaft encoder and a variable speed motor, okay? So now we actually have 2 reactors. Each reactor has 2 augers, so there's actually 4 augers, right? Now, if we were to take this auger, and when we designed this auger, if we hard-coded in the I/O or the configuration like we used to do in the old days, hard code in the name of a global variable here, hard code in a number here, this object no longer is reusable, because now if I hard code those in, all 4 of those augers, the 2 in this reactor and the 2 in this reactor, are all going to be hard coded to this discrete input, to the same discrete input. Obviously, that's not going to work. They're going to be hard coded to the same configuration input, pulses per liter, when that's not going to work. So how do we deal with this? So we deal with the CODESYS gives us a great tool for dealing with the I/O side of things. So instead of mapping to the global variable and then hard coding that global variable, we use the CODESYS full path mapping feature to map the I/O directly to the applicable auger. So here in the I/O now, you may be used to seeing this I/O mapping, and you might have been using global variables in here. CODESYS also allows you to use full path names instead of global variables. And the full path name looks like this. It's just the application.plant, that's the name of the program, .R1, that's the name of the first reactor, .A1, that's the name of the first auger in the first reactor, and .SE1, that's the name of the shaft encoder, .pulse_FI. So when you're typing in this full path name, and I can just do plant dot, and it'll give me R1 and R2 dot, it'll give me A1 and A2 dot, it'll only give me SE1 dot, and then it'll give me all the inputs and outputs for that. But I know which one I want because it's got to have an FI on it. I just map it to the field input. Boom, I'm done. For the second auger in the first reactor, it's just the same, except now it has an A2 instead of an A1. And for the second reactor, same thing, except now it has an R2 instead of an R1. So very simple. We use that to map from the I/O mapping using full path names into each object wherever it's distributed around the design. Unfortunately, CODESYS doesn't give us the same kind of feature for configuration. I wish they did. but they don't. So I've had to create my own, which is available. Basically, this is a CSV file. What happens is, well, after you get your plant design done, you say, write me a CSV file. It creates you this CSV file. They're grouped by function block type. So here is a group for the shaft encoders. This is one line of what would be, of course, many lines. It gives you the names of all the configurable inputs for that shaft encoder. There's only one in this case, pulses per liter, a header, and then it gives you one row for every instance of that function block. It'll automatically put in the default values to begin with. You can then edit those values, read it back in, and it basically does the same thing as this does. It just now writes those values into those positions. So one of these, what does a real one of these look like? So this is one, if you were here on Tuesday and heard the marine hydraulics presentation, this is a configuration file from one of their boats. So notice again, everything is grouped by function. So here's the one for the calc sil oil loads function blocks. Here's the one for the pumps and cylinder systems, kite retriever, and here's the one for the SADE cylinder systems. And so each one of these by the group has its own header that shows you all the variable names. These are all the configurable inputs for this particular function block. And then there's a line for each instance. So here's the one for the Genoa, here's the one for the head stay, here's the one for the jib Cummingham, and so forth. And again, when you first write this, it puts all the default values in there for you, puts all this in there for you. You don't have to type any of this. And then you just go in and change the ones you want to change, read it back in, and you're done. You're configured. Now, if you think about it, if you really think about it, IO mapping is just another configuration. It's something of interest to each instance and should be configured along with all the other configuration inputs for that instance. It's just really another column in the configuration sheet. Maybe two columns. You know, if this happens to be configurable IO, if it could be configured as an input or an output or an analog or digital or something, there'd be another column that says, okay, I want you to be configured as a discrete input in this case. So it might be one or two columns, but it's just really another configuration if you think about it. So all that information is unique to each instance, what physical pin it's connected to, how that pin is configured. That's really unique to every instance. It should really be part of that instance configuration. So in this scenario, an IO module would be just another configurable, reusable function block, just like every other object we've talked about in this chapter. It would have its own configuration inputs for things like its CAN address or things like that. And then it would offer up the names of all its IO points, which would then go to a central mapping service, and then which would connect up the connectivity that we see here. It's just more, and if you would rather have the IO in a different CSV file, that could certainly be done. No problem. You could have your configurations in one CSV file and your IO configurations in another CSV file if you wanted, or they can be all in the same one, whichever you want. So in this scenario, the CODESYS IO wouldn't be used at all. And this gives us the added benefit that the IO could now be updated in an online change. So you don't have to go back and shut the plant down, redo a download if you want to add any IO. It's all programmable. It all could be done in an online change. There's a mock-up here, this OOIP Foundation. If you want to see how that would look, just go there and take a look at that. And now this whole process could be simplified even further with just a little bit of automation added to the IDE. You could easily add just another flag that say, oh, click this. Oh, this is now a configuration input. Do everything that's necessary to get that into a config file, or it's an IO config. Do everything that's necessary to get that to work. And you could do the same thing. Read the config file, write the config file, transfer the PC, and then it would do all that. Don't have that done yet. That requires somebody with a license for the automation platform. Still looking for a partner to work on that enhancement with me. We talked earlier, this is again more part of this chapter, we talked about this naming convention I strongly recommend. This is the one I use. Some people like to put the prefix instead of a suffix so they sort differently. That's fine too, whatever you like, but I find this this to be very useful. It makes it so much easier to know where to connect things up, how to make those connections. Another thing I like to talk about is hierarchical versus flat designs. So if anybody heard the marine hydraulics presentation on Tuesday, you know that I find it best to build a design from small, easy to test and easy to manage building blocks. It's like the engine we saw earlier. You know, Ford had to manage the mining of the copper that goes into the engine. You know, we'd all still be driving Model Ts. The key is to keep the designs down to 1 or 2 pages and to maintain constant levels of detail on each page. You know, and that's why ladder logic is not really a great language for assembling blocks, because it mixes high-level information like what are the blocks with low-level information like, you know, all these detailed connections and, you know, other logic and so forth. That's why, you know, typically if I get a bunch of ladder logic, I can condense that, you know, 10 pages down into 1 page of CFC, because it gets that consistent level of detail. Now, before the chat fills up with hate mail, I have nothing against ladder logic. I think ladder logic is a great language for what it was meant for, relays and timers. It was just never really meant to be a block-based design tool. So CFC is a much better for that. All right, let's talk about the configuration central service library. So this is a little more information on that. So to be able to become a configurable object, the function block needs to extend this equipment base class and implement this config manager interface. Then CODESYS provides this great feature. You just right click on the function block, say implement interfaces, puts them all in there for you. And then you just need to write the code that takes this the string of array and put the variables where they need to go. The same thing, you do the same thing in the provide config, just the other way around. And the titles, you just got to tell it what the titles are so it knows what to fill in at those top of those column headers that you saw earlier. And that's all. And again, you know, this could be greatly simplified with some platform automation that I mentioned earlier. So let's look at how this looks like at a real plant. This is a diagram shows, this is just a small cross section of a refrigerator assembly plant that has a whole bunch of analog inputs. And the analog inputs are going to be spread all over this plant, all over the hierarchy, different levels of the hierarchy. So this one, the top level, nothing at top level. The assembly line has got an analog input. Down at the polyurethane processor for that, it's got a bunch of analog inputs. That processor has tanks for the polyo and the isocyanate, and a bunch of analog inputs in there. So these are spread out all over the place. And remember, this is just a small cross section of the plant. You know, this would be huge. You typically have, you know, hundreds or thousands of these analog inputs spread out all over the place. So how do we deal with those? So this is what, you know, these analog inputs are all these configurable objects. They extend that base class that we talked earlier. They implement that interface we talked about earlier. The library comes with this little auto config visualization. You just start up your program, click this button. It writes the config file. Again, it writes this all for you, puts all the default values in for you, puts the headers in for you, groups them by function block type in here for you. And then you just go in and change the ones that you need to change, and then click the read button. Boom, and it's done. This also, of course, will automatically get read in when the project starts up. So all your configurations will already be there. You can put this config file in your project. It'll download to the PLC when you log in, and then you can do the read button and it'll read those values in. You know, you can also do this read and writing programmatically. So if you've got something in the HMI that can make these changes, anytime when that HMI page closes, just write those values, hit the write button, write those values into this file. This file is human readable, you know, unlike the CODESYS persistence file that is a binary. It's not human readable. This thing's well organized, human readable, very easy to take this to another plant that might not be exactly the same. You could just delete a column or delete a row or delete whatever, a few things that you need to make this thing match the new plant. So just real quickly, the way this works, any object that implements that interface we talked about earlier, it has a method that automatically runs on startup. It basically phones home. It calls the central service, says, hey, I'm here. I'm a configurable object. Here's my name and my path and a pointer to myself. And then the configurator stores all that information in an array. So now the configurator has this array of every object that needs to be configured. So then it can read the configuration file. It can find the matching path name. It has a pointer to that so that it can call, in this case, it would call the accept config method on that, pass out all that information to it, and then in that function block, that method then takes those values and puts them where they belong. And the same opposite obviously happens with the write and with the titles. So that's all there is to it. And and again, same slide, sorry. This could be greatly simplified with just a little bit of automation. If I could get CODESYS to do that, that would be wonderful. All right, let's talk about object-oriented industrial visualization. So this is now the visualization half of this formula. So going back to our example with the pumps, so just like programs can declare instances of reusable function blocks, visualizations can declare instances of reusable visualization blocks. And I call them visualization blocks. I think there are other people call them frames. It's a little ambiguous, so I like to use visualization blocks because they're basically identical to function blocks. They're almost a one-to-one correspondence between them. So I call them visualization blocks. So, in the old days, as we saw earlier, we had to copy pump 1 to pump 2 and copy pump 2 to pump 3. Same thing with the visualization. We'd create a visualization for that pump. We'd hard code in its variable value. We'd make a copy, go in and edit it, hard code in its global variable value. Make a copy of it, hard code in its global variable. A lot of copying, again, mistakes, a lot of work, a lot of nothing fun. We don't need that anymore. So just like function blocks change the way we program, visualization blocks change the way we build visualizations. So here we have, and the way you do that to make a reusable visualization block is to add a var in out to it, or one or more. You can actually have as many var in outs as you want here. So if this block has to get information from 4 different types of function blocks, no problem, just add 4 lines here. This one just only deals with one function block. So here we declare a variable with a local variable name called pump, and we give it, and it's of type pump FB. So it's this type of function block, okay? So now this visualization is tied to this function block. Now instead of hard coding the values in here, pump1.v, we just use this temporary pump.v, okay? So now this becomes a reusable object. And then all we need to do to use that object is we drag it, stick it onto a top level visualization. This is exactly the same, very, totally analogous to adding a function block to a program. You add a visualization block to a visualization. I wish there was better names, but that's what it is. And then this little thing will pop up and you say, okay, which function block instance do you want to associate this with? Okay, we're going to associate this one with P1. Remember, since we're not copying programs, we're just making 3 instances of this function block, and we're associating this visualization with that instance. Obviously, we'd add 2 more of these, and we would tie them to P2 and P3. All right, so applying objects in object industrial programming techniques to both the control and the visualization will make adding functionality to your plant or equipment as easy as add an instance of the function block, add an instance of the visualization, map the instances together, configure the new instances, and run your plant. So in this one, we have this airport loading carousel systems. This one has originally has 5 carousels. We want to add another carousel. So what do? We add another instance, carousel 6. We add another box, carousel 6, connect it up. In the visualization, we originally had 5. We just add another one, configure it, tell it it's carousel 6, and then we configure that. And then we're done. No adding variables to the global variable list, no copying programs or visualizations, no modifying programs or new global variables, no mapping new variables to new visualizations, no adding items to the alarm manager, no adding items to unit conversion list, no adding items to the persistence list, no adding items to the log list, no mapping individual takes to new IO. Just do it and you're done. Add them and you're done. They're completely self-contained, self-reliant objects. They just take care of themselves. So when adding a carousel to your airport becomes this easy, then you have achieved object-oriented programming nirvana, the age of Aquarius, the 7th, the Jupiter collides with Mars, or whatever. I'd sing you a song, but Chris would never let me do another tech talk again, so I'll spare you that. All right, let's talk about object-oriented simulation real quickly. How are we doing on time? Yeah. So I'm a huge advocate of simulation. I know traditionally we would get the control code up to 80% done. and then do the other 80% in the field, right? So I prefer to get it 99.9% done in the lab and then finish it up in the field. I hate to be on the critical path, and I hate even more how the controls group is always expected to make up for time for the delays in the plant construction. With simulation, the code can be completed in parallel along with the physical equipment. 61131 offers great languages for creating simulation models, and CODESYS provides a great runtime for executing those models, control win, and a great environment for running those simulations. So it's all just perfectly set up. So simulation provides the insight that can't be done in the real world. Testing unusual situations, which are impossible or dangerous to do. It provides a high level of confidence. You go out in the field, you plug it in. If something doesn't work, you know it's a wiring problem. You know it's not in your code. It's got to be a wiring problem. And it provides a great way to train operators. This thing can be used as a great operator training tool. And we've seen this, so I'm not going to go through it other than just to emphasize the fact that these are the same connections. So the outputs of your control will be the inputs to your simulator. The outputs of your simulator are the inputs to your control. These are the same full path names that you will use to map your I/O. When you're ready, everything's working perfectly. You just take this out of the build and map in your physical inputs, and you're ready to roll. And we've seen that before. All right, so let's just start to wrap things up here. So I recommend this video. It's actually CODESYS' #1 most popular video in views per year. Just Google object-oriented industrial programming, and these two videos will come up. They're the same video. One's on my site, one's the one that's CODESYS rehosted. And go through that. It goes through soup to nuts, designing an object-oriented industrial program design. It's a tank simulator with a continuous process and some PID loops. It shows how to build a simulator for that, how to build a test bench for that, how to test it, how to use that all to modify and improve the design, how to make that design a reusable object, how to make it a configurable object, and how to configure that object, and how to put 100 or 1,000 of those objects in your plant. So I recommend that. There is a demo version of this configuration library available on the OOIP Foundation. This is a website for sharing objects. That analog input that you saw there is there. Lots of other things there. Obviously, it's a shared site. If you borrow something from there and use it, you're expected to contribute back to it. So that way, this community, these objects, library of objects that are out there will just continue to grow and grow.